Well, what kind of reaction is an acid-base reaction? Do you remember? Double replacement reaction. So what are the products going to be? Do you remember this? Hydrogen hooks up with hydroxide. Sodium hooks up with chlorine, right? So we're going to get sodium chloride and water. Do you remember this, guys? So this is our neutralization reaction, acid-base reaction. But this only works for strong acids and strong bases. Okay? So let's define that a little bit. A strong acid is an acid that dissociates completely. It's actually a strong acid and a strong base. It's a base that dissociates completely, right? What makes it dissociate completely? Maybe it's on our solubility chart, right? So sodium is soluble in water no matter what it's with, right? Okay. So you look at that chart, and that's going to kind of help you. We'll talk more about it in a minute. Any questions so far? All right. So let's just start with the definition of an acid and a base. So an acid is a proton donor. That means he has, what do I mean by proton? A proton is, you know what a proton is, right? What's an H plus ion? It lost its electron. And if a hydrogen lost its electron, what is it? A proton. It doesn't have any neutrons. Well, there are isotopes with neutrons, but most hydrogen atoms won't have a neutron. So if it gets rid of its electron, it becomes a proton. So when we say a proton, we're talking about the hydrogen ion. You with me? And remember we talked about that's what made it an acid, right? If it has a hydrogen ion in it. So why does that make it an acid? Because it has a hydrogen ion that it can donate to something. Does that make sense? So what is a base? It's a proton acceptor. Remember, proton is a hydrogen ion as well, okay? Same. So it's something that takes it. Are we good? So if we look at this equation here, this accepted the hydrogen ion. That's the base. This one donated it, so that's the acid. After it donated it, is it really with sodium? No, it's dissociated, right? And this hydroxide here accepted that hydrogen, became water. Are we good? All right, let's give you some examples of acids and bases. All right. So here's our acids. And the only ones you need to memorize are these strong ones. So here's our bases. We'll just call this a base. Okay? You need to memorize the strong acids and strong bases. Can we see that okay? Should I zoom in? Let's look at the acids for a minute. What makes those strong? That makes it an acid. So let's take a look at strong acid base. Here we go. Strong acid base is an acid or a base that dissociates completely, right? So if we go back to this list, does that dissociate completely? It has to if it's a strong acid. Why does it? Because perchlorate is one of our ions that is soluble, no matter what, right? What about sulfate? Is sulfate soluble? There are a few exceptions, but it's soluble, right? Iodine, bromine, chlorine, those guys are soluble. There are some exceptions, but they're soluble for the most part, right? And nitrate is also soluble. That one has no exceptions, right? That's why these are our strong acids. So memorize those. Good? Phosphate wasn't on that list. Nitrite wasn't on that list. Fluorine wasn't on the list. I think I might have put this on the list, but acetate? Maybe I lied to you. I don't know. Okay, did I put acetate on the list? On the soluble list? Okay, I was thinking I did. All right, so we're good there. So yeah, acetate's not on the list, carbonate's not, phosphate again, cyanide, none of these are on the list. Are these, is this a complete list? Probably not, right? And then strong base, there's only one of them, hydroxide. That's the one we talked about already, right? If it has hydroxide in it, that's a base, we said. Well, that's because that's a strong base. When we dealt with neutralization reactions, we have to have a strong base and a strong acid. But now we're going to deal with weak acids and bases. Okay? So what makes these weak acids? This one right here has sulfate in it. What makes it a weak acid? Doesn't completely dissociate. Okay, great. But also, what makes a base a base? That's right there too. It's also a base. And that's the real reason why it's not a strong acid, because it's also a base. What makes it a base? What's the definition of a base? A proton acceptor, right? Can we accept another proton here? What makes it accept a proton? Or a hydrogen ion? They're oppositely charged, right? So they're going to attract. That's what allows it to accept it. And that's why this is a weak acid. because it has a negative charge. Are we good? And ladies and gents, do you have to memorize these? No, you don't have to memorize the weak acids and weak bases. Just understand why they're acids, why they're bases, right? Acid will donate. So can this still donate a hydrogen ion? Yeah, still has one there. It can donate it, right? And becomes sulfate. But it can also accept one. That's why it's on both lists. We good? Okay. Water is on both lists. Water can accept a hydrogen ion. Let me get rid of all that so it's not too messy. Okay. Water can accept a hydrogen and become hydronium ion, right? Or it can donate a hydrogen and become hydroxide. Are we good there? And this one right here, ammonium, is one maybe, ammonia is maybe one that you should write down. You don't have to memorize, but it doesn't look like a base, does it? It doesn't look like it could accept a hydrogen ion because it doesn't have a negative charge. This is just a covalent compound, right? But if it does accept it, it becomes an ammonium ion. And that's why ammonium ion is an acid. Because it has an extra hydrogen, it can donate and become ammonia. You guys know what ammonia is? It's a cleaning agent. You guys ever dealt with ammonia? Maybe if you have a little brother, grown up with little brothers or sisters or whatever, and little brothers mostly, pee the bed and you smell that up. Right? Okay, there's ammonia in there, but whatever. Anyway, are we good? So again, the things that you need to remember here are the strong acids and strong bases. Questions? Do we have those written down? This list is also in my notes if you want to, whatever. Okay? Okay, a couple other things I want you to know. The hydronium ion is interchangeable with H+. Because basically, basically this is just water with an H+, right? And whenever we have an acid and a base, write this down. Acids and bases are all aqueous solutions. Okay. Why is that? Well, he talked about a strong acid, strong base is completely dissociated, right? You got to have something to dissociate in. It's got to be in water. Good? And last thing before we practice some of this is amphoteric substances. Are both acids and bases. Or both acid and a base. So what's an example of amphoteric substance? water. HSO4 minus. Do you have to memorize these? No, you don't. Just notice this could either take a hydrogen or it could donate one, right? That's what makes it amphoteric. We good? Okay, let's take a look at, any questions so far? All right, let's take a look at the worksheet. Section 1 says to identify the following substances as either acid, base, or amphoteric. Or neither, I guess. No, that's good. Okay. Yeah, I think that's the last day I put on there for you. So, yeah, that's okay. Are there any questions on how to determine if it's acid or base or amphoteric? Yeah, question.
How do you know if it's amphoteric?
So amphoteric is both acid and a base. So let's take a look at this. So this one right here, what makes that an acid? It has a hydrogen ion that it could get rid of. It could still donate that, and what makes it an acid, it's a hydrogen ion donor, or a proton donor, right? That's why that's an acid. Why is it a base? Because it has a negative charge. And a negative charge is attracted to positive charges, so it can accept a hydrogen ion. That's what makes it a base. Since it could be both an acid or a base, we call it amphoteric. Good? Anything else? Okay, ready to move on? If you need something, just stop me. All right. Yeah, question.
Could you split up for just 1 second? Sorry.
No, you're good.
So would you say that, so for the, like I understand looking for a negative charge to be a base, then how would you necessarily like always determine that a hydrogen ion can be donated? Like that was my,
Because this is the cation in this ionic compound. How do you know it's ionic? There's no metal in it. Because this is a polyatomic ion. We should be able to recognize that.
I was thinking like solubility wise.
It's not a strong acid or a base. It's actually a weak one. But it's still an acid or a base. Good?
Yeah.
Thanks for stopping me. We good? All right. So we gave an equation for a neutralization reaction with a strong acid and a strong base. Now let's do one that doesn't have a strong acid or a strong base. H2SO4, that's a strong acid. But H2O breaks down to HSO4 minus and H3O plus. So on the left, first of all, is this an acid-base reaction? To be an acid-base reaction, we have to have both an acid and a base. Do we have an acid up here? Where's the acid? That's one of our strong acids. We should just memorize that. But how do you know it's an acid? It has H plus as the cation, right? That means this would have to be a base if it's an acid-base reaction. Is that a base? Yeah, water's amphoteric. So that is our base. It's not a strong base, but it's a base. Here's another way to tell. Which one of our products does this one turn into? That one or this one? First or second? First one. Right? And what's different? It lost a hydrogen ion. That means it donated a proton or donated a hydrogen ion. So that's the acid. You following me? And this one right here turned into that one. And what did it do? It accepted a hydrogen ion. We good? So if you can kind of see what's happening to the hydrogen ions, that's how you tell which one is the acid, which one is the base. Questions? Yeah.
In the beginning, you about H2SO4 being the strongest?
It's a strong acid, not necessarily the strongest.
Oh.
So if we look at our list, there it is. It's a strong acid. So if we memorize all of those strong acids, there's 1, 2, 3, 4, 5, 6 of them, and one strong base, memorize those, then all the rest are weak-ish, right? Anything else? Okay, let's do another one. Excuse me. H. Thanks. HSO4 minus plus H2O breaks down to SO4 2 minus and H3O plus. Go ahead and determine which one the acid, which one the base is. This time, both of the reactants are amphoteric, right? So use the reactants to help guide your thinking. Which one donates a proton? Which one accepts a proton? That's how you tell. Got it? So, what one does this one turn into? Which product? First or second? First, right? And then, of course, this one turns into the second one. Which one donates a proton? HSO4 donates a proton. That's why it doesn't have one anymore. Are we good? And the water accepts one and becomes H3O plus. So that's the base. We good? Anybody notice something weird though? Is this an acid or a base? Does it have an extra H plus it can get rid of? Yeah, it does. Is this an acid or a base? Has a negative charge. Can it accept a proton? Yes. Negative charges can accept a positive charge, right? So the acid turns into a base, and the base turns into an acid. Good? So we call these conjugate acids. And conjugate bases. So a conjugate acid is the product of a base, and the conjugate base is the product of an acid. So the conjugate base would be this one right here. Oops, sorry. And the conjugate acid would be this one right here. Does that make sense? So if you have an acid, you're going to have a conjugate acid, or you're going to have a conjugate base. If you have a base, you're going to have a conjugate acid. Ready to try another one where you put all of them down there? Let's do it. HCl plus NH3 breaks down into NH4 plus and Cl minus. So determine which one is the acid and the base, which one is the conjugate acid, which one's the conjugate base. Or should we do it together? How you feeling? Together?
I think I'm starting to get it.
Okay.
I don't think I do it. I think I'm starting.
All right, let's do this one then. Okay? HCl turns into what? Cl, right? And NH3 turns into NH4. That means HCl and Cl go together, and NH3 and NH4 go together. So which one's the acid? HCl or NH3? HCl is the acid. So what does that make Cl? Conjugate base. Right? Therefore, this one's the base, and this is the conjugate acid. And let's make sense of that. Is this one an acid? Does it have an extra hydrogen it could donate it if it needed to? Yeah, the H plus, right? Has an extra H plus. If it goes back, the acid turns into a base. This one right here is a base because it's a negative charge. If it gained a hydrogen, it can go back and turn into HCl, right? We good? All right, let's take a look at our worksheet. Let's do section 2. There's 3 examples here. Go ahead and identify the acid base and conjugate acid, conjugate base. The answer's up here if you want to see how you did. Any questions? Do the last one? Okay.
Last one will, like, yeah, I just wanna understand, how it donated.
Okay. So HBR turned into this one, right? And this one turns into this one. Are you wondering because of that guy right there?
But, yeah, and because it's like two hydrogens, so I think I got tricked because I'm like, okay, so there's a hydrogen here, an AOH, and then like,
So there is a hydrogen here, but this is a hydroxide ion,
so, okay,
right? And that's the difference.
okay,
This is the cation, and when hydrogen is the cation, that's what makes it an acid. When you have hydroxide, that's the strong base. Okay?
well, so hydroxide, just generally speaking, will denote a strong base,
Always.
always.
That's the only strong base that we have. Okay? So that's kind of nice. So if this is a base, it's going to accept a hydrogen and become water. Right?
Okay, that makes sense.
This loses it, and it's going to be in solution with all this other stuff. So it could pick up a sodium, right? In real life, it won't. Why not? Because it's just going to stay dissociated in water, right? But, okay. We good?
So is hydroxide always a base, but it wants to do water most of the time?
If it accepts a, yeah. If hydroxide accepts a proton, yeah, it becomes water every time. We good?
Yeah, I really like hard and fast rules, so like seeing hydroxide,
Yeah,
I'm just like,
yeah, that's nice.
cool. Thank you.
Yeah, you bet. Anything else? All right. Let's move on to the fun stuff, shall we? Well, we've done this before, so it's just review, right? No big deal. Hopefully. So let's say we have HCl plus calcium hydroxide goes to H2O plus calcium chloride. And let's say we have 1.5 moles of hydrogen chloride, and we want to know how many moles of calcium hydroxide we will form. Do we know how to do this even if it wasn't an acid-base reaction? We should. This is just stoichiometry, right? Where do we start? Okay, 1.5 moles. Start with what we know, okay? What can we convert to? We could convert to grams, but we want to convert to moles of this, right? So what should we do next? What? Balance the equation. We better have a balanced equation, otherwise we don't know the mole-to-mole ratio, right? Good catch. Okay? And so here we have 2 chlorines, so we better put a 2 right there. And we have 2 hydroxides and 2 hydrogens, so we better put a 2 right there. Good? All right, so what's the ratio? What goes on bottom? 2 moles of HCl to 1 mole of calcium hydroxide. That goes away. Is this what we're looking for? And we're done. Does this have anything to do with acid bases? No, it's nothing, right? We do the math and we get 0.75 moles of calcium hydroxide. Can we all do stoichiometry? Wanted to start simple? Is if we can't do this, forget about the rest of the lesson. Are we okay? So just remember, use the mole roadmap. Convert grams to moles, moles to moles, moles to grams, or whatever, right? Follow that. If it's going away from where we're trying to get to, then don't do that. Okay, that's it. All right, you ready to spice it up? Should we keep it a little bit simpler? I mean, still simple, but a little bit more than that. We're not spicing it up yet. We'll just go to the next step. Here we go. So let's say instead of we have 1.5 moles, let's say we have 39 grams of HCl, and we want to go to grams of, find out how many grams of calcium hydroxide is needed to completely react with it. Where do we start? We already have a balanced equation. It's the same equation. So yeah, let's start with 39 grams of HCl. And what are we going to convert to? Look at your mole roadmap. What does it say? When we're at grams, the only thing we can convert to is what? Do you have this? Pull it out. The only thing we can convert to is moles from grams. Using what? Molar mass, yeah. And the molar mass of HCl is? Not quite. Chlorine has a molar mass of 35.5. You looked at the atomic number, yeah. Okay. So we got 36.5 grams of HCl. Y'all with me? To 1 mole of HCl. That goes away. Now we have 1 mole of HCl. What can we convert to? Moles of what we're looking for. We just copy and paste that guy right there. Same equation, right? Yeah. 1 mole of calcium hydroxide to 2 moles of HCl. Moles of HCl go away. And now we got to convert to grams, right? Moles to grams. That's what we're looking for. 1 mole of calcium hydroxide has a mass of 74 grams of calcium hydroxide. Now I'm going to ask you a question real quick. On the test, is it better to round your molar mass or not round it? Probably on the test is to not round it, right? We figured that out the hard way, sorry. So maybe we shouldn't round it. It's probably 74.1 maybe. We can round it a little bit, I guess, instead of 0.09. It's pretty darn close, okay. And the reason I said to round it is because it's different depending on whatever periodic table you use. So In real life, it's probably not that big of a deal. But yeah, for your test, for your exam, maybe not round it to get closer to the answer that they're looking for. Okay? Okay, moles go away. We're left with grams. That's what we're looking for. So we can calculate it, and we get 39.6 grams of calcium hydroxide. Good? Okay, you ready to go to the next step? So that's generally as tough as it gets in stoichiometry, right? If we could do that, we could do all stoichiometry. Now we're going to start with something maybe what we did last unit. A solution, right? Did we do solutions last year? Yeah, okay. So we're going to have 2HCl plus calcium hydroxide. Gives us this, basically the same equation, right? H2O plus calcium chloride. And we want to know how many moles of HCl that react with 350 milliliters of a 0.200 molar concentration of calcium hydroxide. So, how do we go about solving this? We want moles of HCl, and we're starting with a different substance. So what do we need before we can go to moles of HCl? Look at the mole roadmap. We have to have moles of calcium hydroxide. You with me? And then once we have moles of that substance, we can convert to moles of HCl. Okay? All right. Is there any moles in the information that we're given? Yeah, where is it? Remember, molarity is moles over liters, right? Okay, so maybe let's start there. A 0.200 moles of calcium hydroxide to 1 liter of solution. Now we have moles on top. That's where we want it, so we're not going to do anything with that. But we want to get rid of liters. What should we convert it to? Yeah, we got to go to milliliters, right? So 1 liter is the same as 1,000 milliliters. Liters goes away. Now we have milliliters, but we also have 350 milliliters, right? That goes away. And we're left with moles of calcium hydroxide. We can keep going, or we can find an answer and then start up again. What would you rather do? Your call. Anybody have a preference? I like to just keep going, but that's me. I had students that like to just stop and start again. You okay with keep going? Okay. So we don't want moles of calcium hydroxide in our answer, and that's what we have. It's the only unit that's not canceled. We want moles of hydrochloric acid. So now we use our mole-to-mole ratio, right? So 1 mole of calcium hydroxide on the bottom cancels out with what on top? 2 moles right there. Our coefficient of HCl is 2. 2 moles of HCl moles of calcium chloride calcium hydroxide go away. We're left with moles of HCl. That's what we're looking for. We're done. Other than we multiply and divide, and we should get 0.14 moles of HCl. Was we able to get that one? Okay. So that's just a one step up. Let's see. Should we do another one? Or do you want to try practice on your worksheet? One more? Yeah, let's do one more. Okay, so it says, okay, if we have how many liters of HCl of a 0.125 molar concentration of HCl would need to react with 350 milliliters of a 0.200 molar concentration of calcium hydroxide and we're dealing with the same stuff, right? Same equation. We have 2HCl plus calcium hydroxide gives us 2 H2Os plus calcium chloride. So where do we start? Should we start with liters of HCl? Just to see what we actually need, maybe? Or we can start with this, right? 0.125, and we change molarity to moles of HCl per liter of solution. What do we need to be able to calculate volume of solution? We need to cancel the moles of HCl, right? So we got to know moles of HCl. You with me? So I'm going to erase all that. We need to calculate moles of HCl first. We kind of just did that from here, didn't we? You with me? Because those are the same numbers basically, right? So we do all of that what we did, and we found 0.14 moles of HCl. And now we can put 0.125 moles of HCl per 1 liter of solution. That's what we're looking for. Right? So just one additional step. We good? And of course, that would give us a 1.12 liter solution of HCl. Does that make sense, or did it?
I think it actually further confused me, because
How would that?
I saw you went back to the,
Because this right here, we have 350 milliliters of a 0.2 molar solution. Well, that's what we had in the previous problems. It's basically the same problem, but now I don't want moles because in general, we don't care how many moles we get, right? That's not really useful. But maybe it says how many, what volume of this concentration do we need? Because we start with a concentration of our acid to dilute it, or to not dilute it, but to react. And we want to know, well, how much do we need? Are we good? So that was just an extra step. All right, let's practice one that's on our worksheet. So on section 3, let's just try one of those. You want to try one by yourself, or what are you feeling like? And on section 2, we have 3 equations. Those 3 equations go to the same 1, 2, and 3 on section 3. So you need an equation to do this. Those equations are on section 2. Follow? If you want to do a more complex one, do number 3. Or if you don't want to do a complex one, you could do number 1. Any questions? Who needs more time? Okay, carry on. Doing good? Okay, how are we feeling? Any questions before I move on? Okay, let's move on. All right, next thing we want to talk about is pH. pH stands for power of hydrogen. Okay, great. And when we talk about power of hydrogen, that's really talking about logarithms. You guys remember logarithms? Math 10, maybe? Okay, I'm not going to have you do, I don't need you to know all the rules of logs. All I need you to know how to do is use your calculator function that says log on it. Are we good? Okay, it's not too complex. So the first equation, in fact, before we talk about the equation, the pH scale goes from 0 all the way up to 14, where the 0 side is the acid side, and the 14 side is the base side, and right smack in the middle at 7, that's water. No, water's amphoteric, it's both acid and base, right smack in the middle. Good? So the closer to 0 it is, the stronger acid it is. Closer to 14, the stronger the base it is. Good? All right. The equation is on your reference sheet. You don't have to memorize it. That's nice. In fact, all the equations that I'm going to give you are on the reference sheet. It's kind of a nice luxury, right? So to calculate the pH, it's just equal to the negative log of the hydrogen ion concentration. Remember when you put it in brackets, that means it's concentration, right? And another equation that we could use is the POH, which is equal to the negative log of the hydroxide ion concentration. Okay. Have you ever heard of finding the POH of like a tub? Or not a tub, but like a hot tub? I haven't heard of POOH. Have you guys? But pH, right? Find the pH so that it's not too acidic or too basic, okay. So we're just using this one to find this one generally, okay? So let's do an example. Simple example, but let's start simple. Okay, if we have a 0.015 molar concentration of H plus ions, what's the pH? Make sure we can calculate this. So again, pH is equal to negative log of the hydrogen ion concentration. So that's equal to negative log. Hydrogen ion concentration is 0.015. So plug that in your calculator, and we should get 1.824. Make sure you can get that in your calculator. We good? Everybody getting this? Y'all find the log, right? Okay. So that's if we have the hydrogen ion concentration. Most of the times we don't. So let's look at some examples where we need to find that. Okay? Does you have any questions right now? Okay. So we want to find the pH of a solution that contains 0.0125 molar solution of HCl. How do we do that? We know the concentration of HCl, but to find the pH, we have to find the concentration of H plus. Well, can we change this moles to moles per liter? Start with 0.0125 moles of HCl per 1 liter of solution. Are you following me so far? This is kind of review. All right. Now, remember when we first started talking about stoichiometry, I said if we have water, what's the ratio atoms to atoms of hydrogen to oxygen? 2 atoms of hydrogen to 1 atom of oxygen. Remember doing this? Can we say that that's equal to 2 moles of of hydrogen for every 1 mole of oxygen? Is that true? Yeah, we We calculate this and prove that this is true. So, can we convert this to moles of H plus? If we have 1 mole of HCl, how many moles of H plus do we have? 1. There's 1 of these for every 1 of those. You following me? So that goes away. Now we have moles of H plus per liter of solution, which is the same thing, right? So if we can see that this is a 1-to-1 ratio, do we have to worry about doing this? No, we don't, right? But if it makes us feel better, then do it, okay? So to find the pH of this, it's just going to be negative log of this, right? 0.0125, and that's going to equal 1.9. Are we okay so far? All right, that's how we're going to calculate the concentration of H+. What if we had 0.0125 moles of H2SO4 and we wanted to find the pH? Is it a 1-to-1 ratio? No. So it's for every 1 mole of H2SO4, sorry, I should say moles per liter, right? 1 mole of H2SO4, how many moles of H plus? 2, right? So we multiply that by 2 and get 0.025 is our concentration of H plus. We put that in our calculator. Oh, what's going on? Negative log of that answer. And I don't know what we get. 1.6. What units do we have? No units for a pH, because it's just a power, right? So that's kind of nice. Any questions so far? All right. Now, sometimes we're dealing with something like this, where we have, we want to know the pH of a 0.0105 molar concentration of magnesium hydroxide. Is this a 1-to-1 ratio, or what is it? Does this compound have H plus in it? No, it does not. That's where we get into finding the POH. Can we find the POH of this? Negative log of the hydroxide ion concentration. And what's the ratio? For every 1 of these, we have 2 of those, right? So we got 1 mole of magnesium hydroxide for every 2 moles of hydroxide. And again, we can just say this is moles per liter, right? So we multiply that by 2. And we get negative log of 0.021. You following? Questions? So I just put the answer of this right here. Following?
Yeah, that, this tracks.
Oh, good, good. Okay. So the POH is 1.68. Is this what we're looking for? No, we got to find the pH. So we got another equation, and it's given to you on the reference sheet. pH plus POH equals 14. Y'all understand where that 14 comes from? The pH scale goes from 0 to 14. So the pH plus the POH equals 14. How do we calculate the pH? Subtract POH to both sides. And we got it. So 14. So the pH is going to be 14 minus the 1.68. And that gives us 12.32. Good enough? So if you're dealing with a base and you want the pH, that's the process. So let's look at our worksheet. Any questions on that? Okay, on section 4 of your worksheet on the back side, it says calculate the pH. Which one of those do you want to do together? Should we try the bottom one on the right side? That one looks icky. So we start with 2.3 grams of calcium hydroxide in 1.85 liters of solution. So we got to calculate the pH. Where should we start? Since this is a base, hydroxide, we're going to find the POH first, right? All right. Before we can find the POH, we got to find the OH concentration. Is that right? And before we can find the OH concentration, we need to know the concentration of this. Do we remember how to find the concentration? Moles over liters, right? The amount of solute over the amount of solution from last unit. So what's our solute? 2.3 grams of calcium hydroxide. That's the amount of solute. The amount of solvent solution is 1.85 liters. Now what do we do? Convert grams to moles, right? Got to have moles per liter. And the molar mass is, we did this before, 74.1 grams of calcium hydroxide to 1 mole of calcium hydroxide. Following? Now we have moles per liter. Now what do? We have concentration of calcium hydroxide, but in the end we want POH is equal to negative log of hydroxide ion concentration. So we got to find out the concentration of OH. How do we do that? Yeah. For every 1 mole of calcium hydroxide, we have 2 moles. Everybody get that? We have 2 to 1, right? So moles of calcium hydroxide go away. We're left with moles per liter of hydroxide. That's what we're looking for. We can find that answer, put it in here. So what do we get? Somebody calculate that.
.062.
I don't know. I'm getting something different.
Isn't it, 0.0335?
Yeah. Are we good? We good, Andrew? Okay. So that's our molar concentration of OH minus, so we're going to put that in to the negative log, right? And so our POH is what? 1.47? So how do you calculate the pH? Because that's our question. Make sure we... So when we have multiple steps like this, ladies and gents, make sure you go back to the question. What is the question asking? Make sure you don't just, okay, there's my answer, I'm done. A lot of times multiple choice, that's what they'll put in there. Yeah, 14 subtract 1.47, 12.53. Good? We're ready for the big kahuna? Everything all together? Okay. Which one do you want to do? 1, 2, or 3 on section 5? I taught you everything you need. So which one do you want to do? Whoever says it first, that's what we're doing. Okay, the third one?
Yeah.
Okay, why don't you get it started? All of you. All right. How we coming? Is this equation balanced? Yeah. Good. We want to know the pH of a 1.25 liter of lithium hydroxide solution that neutralizes with 2.32 liters of HBr with a concentration of 0.0678 molar. Right? Okay, so what should we start with? We want to know the pH of what? Of this, right? Okay. So what do we need if all we have is the liters? All we have is liters of LiOH. We need the pH of LiOH, right? So what do we need? Yeah, we need moles. We need concentration, right? To find pH, we got to have concentration. All right, so we need initially moles of LiOH. Are we okay with that? Okay. So what can we calculate? What can we do first? Find moles of this. Can we find moles of HBr given that information? And then we use the mole-to-mole ratio, right? You see my thinking here? How I'm, okay. And if you don't, just start with something. See where it leads you. So 0.0678 moles of HBr per 1 liter of solution. That's this, right? Now what do we do? We use that. We can't use that anymore. Do we want liters of HBr solution? No. How do we get rid of it? Multiply by 2.32. That goes away. Good. Now we have moles of HBr. What can we convert to now? Moles of LiOH. What's the mole-to-mole ratio? 1 to 1. Good. 1 mole of HBr to 1 mole of LiOH. That goes away. Now what can we do? We use everything but this. Can we use that yet? We have moles of LiOH, and this is liters of LiOH solution. Can we find the molarity of LiOH? Yeah, right? So just divide that by 1.25 liters, and now we have moles per liter. Do you want to find an answer or keep going? Keep going, okay. So now we have, and we could just put a 1 right there, yeah? Now we have moles per liter, or molarity of LiOH. And what's the mole-to-mole ratio of OH to LiOH? 1 to 1, right? So that's 1 mole of LiOH to 1 mole of OH. That goes away. And now we have moles per liter of OH concentration. So what can we find with that? The POH equals negative log of the OH minus concentration. So now we can calculate the OH minus, which is 0.1258 molarity. Yeah? Am I going too quickly, or are you following me? And I know it's a lot of steps. Questions? Okay? So that's going to be negative log of 0.1258. And that's going to give us a POH of 0.9. And the pH is what we're looking for. That's 14 minus the POH, 13.1. How you feeling? A lot of steps, but just take one step at a time. Questions? Good? Okay, that's it, ladies and gents. Go practice this. Don't forget to study this. Revisit this within a day, right? Thank you very much for coming. Drive safe and have a great night.